Hello everyone, and welcome back to the Kohi Game Engine series. Today we're going to take a look at normal maps. So before we jump into the video, I'd like to thank a few special people. We have the partners of the channel. Those are the highest tier of support through Patreon or YouTube memberships. And those partners are Caden, Eearslya, Joel, Kyla, and Wensheng. Also supporting the channel are all these other fine people on the screen. Thank you all very much for your support. It is greatly appreciated. If you'd like to support the channel and support my work, feel free to have a look at the YouTube membership, or if you prefer Patreon, you can check out patreon.com/TravisVroman. Okay, so last time we took a look at specular maps and discussed how specular maps add a little bit of reflectivity and allow us to control the reflectivity of different materials. And today we're going to add something called normal maps. And normal maps will really enhance the realism of our surfaces and give us a more three-dimensional looking texture surface on our geometry. And so, what is a normal map? Well, a normal map essentially looks like this. It's a texture that gets fed into our system, and the colors on this are used to generate various normals for a surface. So if we refer back for a second to our previous video's graphic here, we have our normal, our reflection, and then the I vector, right? And this basically takes in our sunlight and calculates the direction of reflection for our specular reflection. And so this works perfectly fine on a perfectly flat surface. A normal map takes this one step further. A normal map basically takes your surface and makes it look bumpy like this. If you picture this as still looking at the geometry from the side, our geometry is here in this brownish color, and then our normal map will add detail to it like this blue line here. Add some bumpiness. And what that will allow us to do is show a little bit more detail due to the way that light bounces off materials such as this. So something super bumpy is going to show those bumps by reflecting the light in different directions based on what the current surface that ray of light is hitting looks like. So your light winds up bouncing off the surface in all different kinds of directions. Again, this is sort of an oversimplified graphic, but it'll give you sort of an idea of what we're going to achieve here. So we're still going to have completely flat geometry, but the normal map allows us to redefine the normals of the surface as we go. Instead of just being stuck to a single normal like this, we have a lot of different normals that look something like this. So if you take a look at a normal map, it looks a little bit something like this. And this actually is encoded with data that we're going to use to generate normals. So typically speaking, the way that most normal map implementations work is you use the R, G, and B channels to indicate your normal. So your red channel is going to be used for the x-axis, your green channel is going to be used for the y-axis along the image, and your blue channel is going to be used as the z-axis, which would be sticking straight out into the screen in this case. So you'll notice that a lot of normal maps have this sort of pinkish, purplish hue to it, and that is predominantly why. Is because most of the time your normal map is going to be predominantly pointing outward from the surface, and that's going to make it mostly blue. So again, what that does is you take this, you apply it to the surface that's flat like this, and you wind up getting a bumpy surface that looks like this. So how do we accomplish this? Well, we need to add a little bit more information to our geometry. So for basic directional lighting and specular highlights, all we really needed to know was just the normal of the geometry. However, in order to generate this bumpiness, we actually need to know two more pieces of information. And those two pieces of information are called the tangent and bitangent. And these indicate how the map is actually applied to the surface of the geometry. So your tangent typically runs along the x-axis of the texture, and your bitangent typically runs along the y-axis. And then of course your normal is sort of popping out of the texture. So if you picture this flat plane here, this is how the tangent and bitangent are aligned. So typically your tangent and bitangent are calculated based off of your actual geometry itself. So typically you'll take two edges and you'll use those to actually generate your tangent. And then you can take that same information and use that to generate your bitangent. So we'll kind of jump into that here in a second. But that is the overall view of what we need to add to our shaders to support what we need. So we need, to recap, we need a normal map sampler to be added to our shaders. We need to be able to pass in tangent and bitangent information. The first thing that we are going to touch on is in our math types. We have added two things here. We have added color and tangent. Now wait a minute, I just said that we are going to add tangent and bitangent. What's this color all about? Well, the color is something we're actually not going to use right away, but we want the ability to also be able to set colors on materials, and I wanted that to be included as well. So I'm going ahead and adding it now, and we'll use it in a little bit. But more importantly, we are going to focus on the tangent for now. So we're only passing tangent here. Why aren't we passing bitangent? This is because we can actually calculate the bitangent based on the normal information and the tangent information that we pass in. This is because these directions are all orthogonal to one another. So we can actually take the normal and our calculated tangent and use the cross product of those to get our bitangent, which is exactly what we're going to wind up doing. So in our Vertex 3D, all we have to do is add tangent. And again, I've added color for additional utility in the future, but really the only one we need right this minute is tangent. Okay, so how do we go about calculating out this tangent? Well, we're adding a new file to our math sort of library here called geometry utils. And we're going to use this to perform various geometry math functions that we're going to need. So right now we only have two of them, and only one of these we're actually going to wind up using, but we are going to need them both at some point, so I went ahead and added them both. So the one we're interested here is this generate tangents. So this calculates tangents for the given vertex and index data. So basically what we do is we pass all of our vertex information and all of our index information, and we loop through those and we generate the tangents within those vertex 3Ds. And the way that we do that is we loop through the indices 3 at a time, because we have 3 vertices per triangle, and we want to process this a triangle at a time. So our index array is always going to give us this in triangles, so it's safe to assume that we can just iterate these from top to bottom at going 3 at a time, and we'll be working with individual triangles here. So what we do is we detect we detect 2 edges of the given triangle that we're dealing with, and that will actually give us a direction in space for what the normal and tangent looks like. We calculate some deltas based on the UV coordinates, and we take those, and down here we calculate the tangents based on the edge and the deltas between the texture coordinates, and that is what gives us our tangent information. Now in here we could also calculate the bitangent if we wanted to. It would be very easy to add that calculation in here as well, but again, like I said, we could just do this in the shader every once in a while and not have to pass all that data over to the GPU, so that's what we're going to do. Now if you're interested in the specifics of tangent generation, that's not something I'm going to cover in this video just for the sake of time. I may make a separate video that goes over the math specifics of all of this, but for now, this is the algorithm to actually calculate that. One more thing that I want to point out is we have a calculation down here that is done for handedness, And this is to handle situations where your normal map may be inverted or flipped or mirrored, because there are a lot of pieces of geometry that actually do this to save on texture memory. You'll typically reuse the same normal map from one side to the other. But if you think about it, our RGB represents our XYZ directions. So if you flip that, the actual data is going to be wrong. And so this handedness basically uses the texture coordinates to figure out whether or not those normals have been flipped. And if they have been, we go ahead and we apply a -1 or we apply a 1 respectively, based on whether or not that's flipped. And we actually use that in our shader to go ahead and correct the normals so that they're at the correct orientation when we go ahead and load the geometry. So that way it handles anything that is potentially flipped. And this allows us to also handle that without having any branches in our code or any ifs or anything like that. So this is just packed into the vector4w component. So our tangent lives in the XYZ, the handedness gets packed into the W component, and then we use that on the other side in the shader. Finally, we go ahead and we apply the tangent to the 3 vertices that we are looking at for that particular iteration of the loop, and we just rinse and repeat. Here we have the normal generation, and again, it just uses the edges to generate a normal if we don't already have that information. So if we are using or importing geometry data at some point that does not actually include normal information, this function will allow us to do it. Again, I'm not going to cover the specifics of this. I'm just going to include this here as a utility in case we need it in the future. So that is geometry utils. So next, let's have a look at our shader updates. So first thing we're going to do is start off with our material shader config. We have added a few properties into this. So in our attributes, we've added the in color and in tangent. Again, we're not using the color right now, but we've gone ahead and added it. So this will be in slot number 3. So we have 0, 1, 2, 3, and 4. Furthermore, we have also added a sampler in here for our normal texture. And again, this is an instance level uniform. So that is it in terms of our shader configuration. Next, we'll take a quick look at our Vertex Shader. So our Vertex Shader has in slots 3 and 4, our in color and our in tangent. Next, our out DTO actually has our color and our tangent as well, because we're going to be supplying those to the Fragment Shader. So after some calculation, we'll go ahead and supply those. So we have those added to our output here. And of course, the input on the other side. And right here, we just pass through the color. And a little bit further down, we actually are performing some calculations here on our tangent. So we're basically taking this tangent and applying the model to it. So our model matrix, we're taking that and applying that to the XYZ of the tangent, and we're leaving the W as it is. As a small optimization here, we've gone ahead and saved off the matrix 3 version of the model so that we don't have to keep calling that, and we just use it down here in the shader. So we've changed our normal code to just reference that saved off variable, as well as our tangent here. Moving on to our fragment shader. We have added another constant for our sampler index, so that is now 2. We've increased our samplers by 1. So now we have up to 3 samplers. We've gone ahead and added in the input DTO the color and the tangent. And now we have something called the Tbn, which is a matrix 3. And this is something I'm probably going to wind up moving to the Vertex Shader, because it doesn't really need to be in the Fragment Shader, but for now this will be fine. So the Tbn matrix is a matrix that is made up of the tangent, bitangent, and normal, respectively. This is used to take our normal map from the sort of texture space into our world space. And so we go ahead and we set up a Tbn matrix based on that. So before we can calculate that, though, we have to do a couple of things first to our tangent, and then our bitangent calculation needs to be done. So the first thing is we take our tangent in, and we set that equal to tangent minus the dot product of tangent and normal, and then we multiply it by the normal. And so this is something known as the Gram-Schmidt process. Again, I'm not going to go into the math specifics on this because I'm probably going to touch on that in an appendix video. But basically this makes the tangent a little bit more accurate for very little cost. So it makes it look a little bit better. The end result looks a little bit better. Next, since we have our tangent and our normal, as I mentioned before, we can calculate the bitangent by taking the cross product of our normal and our tangent. So we take the x, y, z of the tangent, because remember the tangent is a vector 4. So we take the cross product of those things and then we multiply it by that w. So if you recall, in my previous explanation, we have this w component that is used to indicate our handedness, which is either a positive or a negative 1. This is where that inversion is done if it needs to be flipped because the normals were mirrored in the geometry. So this is what handles that to keep that correct. And then of course we set up our Tbn matrix using our tangent, bitangent, and normal passed into the mat3 constructor, and that gives us our Tbn matrix. We then have something we're going to call our local normal, which is essentially our normal map sampled using our same texture coordinates, and we're just going to use the RGB of that, and we shift that from being a -1 to +1 value to being a 0 to 1 value, because we don't really want to be dealing with negative numbers when it comes to normals. So we use this to shift that, and then we go ahead and we multiply that by the Tbn matrix to give us our final normal. So instead of using the normal that's passed in, we are taking that normal and combining it with the tangent and the bitangent and the normal map, and we are getting a final normal on that, which gives us a per fragment specific normal. This is how our normal is applied in our normal maps. And then that just gets passed through as normal to our directional light calculation. So nothing in there actually has to change, because all we're changing is the normal input to that function. One thing I would like to point out, though, is that instead of passing the in-DTO normal here, we are passing our newly calculated normal. So we're just changing the input to that, but this function here remains exactly the same. And that is the crux of the changes, at least within the shader itself. So a couple of other quick updates. These are probably updates that you are expecting, but we'll go over them nonetheless. So first things first, in our material loader, we have actually added our normal map here. So if we have a variable called normal map name, we go ahead and extract the value out of that. On resource types, we've added another texture map called normal map. A little bit further up, we have also added another texture use for normal maps. So this one is 03. In our material system has also received some updates. So all the way at the top, we now have a index or a location for our normal texture. We go ahead and we invalidate that here. Then a little bit further down, we go ahead and extract it here. In our apply instance, we go ahead and apply it here. And then in our load material, we go ahead and get the normal map here. So just like the same process we use to get our diffuse map and our specular map, we get our normal map here. We've also added something for our texture system to get a default normal texture. We'll touch on that in just a second. Before we move on, we also release the normal map texture when we destroy the material. A little bit further down, when we create our default material, we are also obtaining the default normal texture there as well. Really quickly, we'll go to the texture system. So we've added this get default normal texture. It returns the address to the default normal texture that we've added to the state pointer. And of course, in our create default textures, we have now added a entry to create a normal texture. This normal texture has default values of 128 for the R and G channels and 255 for the B and A channels. So here, this is basically what a completely flat generic normal map looks like that applies no different normals whatsoever. So it gives us this sort of bluish, purplish kind of color. So that is sort of the default value for a normal map. So we go ahead and populate the entire image with that. And then we go ahead and store it off here, of course, with its own default name of default norm. And naturally, when we destroy the default textures, we make sure to go ahead and destroy the default normal texture as well. Obviously, we have added those definitions here to the H file for that. So here's the definition of the function, and then at the top here is the definition of the map name itself. And finally, our last set of changes is, as you may have expected, in the application. So the first thing that we've done is all the way at the top, we've gone ahead and added a temporary include to geometry utils. And I say this is temporary because, again, we're just sort of hard coding some geometry that we're generating here just to get things up and running. Eventually, this will be a process that's automated, yada, yada, yada. Eventually, this will be a process that's automated and we won't actually have to do this. But for now, we include the geometry utils here. And if we go here to our event, we've added another section for normal names. So this is just like we did for the spec. We have underscore NRM versions of all of our textures here. So we have our cobblestone, paving, and paving 2. And as we cycle through this, now we have the default or the diffuse map being changed out, the specular name, and the normal name. And of course, we acquire the new normal texture and release the old one, just as we're doing before. Again, we're actually going to be adjusting this to work a little bit more robustly here in the near future. But this is just sort of to verify that all of our textures and our texture swapping is working as designed. And last but not least, in our temporary code and application within application create, we've added a call to our geometry generate tangents. We simply pass the configs, vertex information, and index information. And this goes ahead and populates that with our tangent information. So let's go ahead and post-build this to rebuild our shaders. And we'll go ahead and clean and rebuild the application. And I'll go ahead and run. And we'll note here that we don't actually see anything different. And this actually means that things are working as designed. We do see our specular texture appearing, but since we're using a default normal texture for this particular material, it doesn't look like anything because it doesn't look like anything has changed because nothing really has changed. We're still using the basically the normal that's passed in by applying that default normal map. But the way that we can actually see the difference is if we press T to change out the textures. Now we can see that we actually have our normal map applied. So we can see our specular and our normal all working together for a nice, more realistic shaded surface. So we can see all the bumpiness of the surface reflecting in the light there. And it gives us just sort of a much more realistic look. Now, obviously, I have the settings for this exaggerated, so it kind of looks like it's a wet texture versus how it might actually look if it were on a sunny day. But the exaggeration makes it a little bit more obvious what the actual changes are here. So if we go ahead and cycle to some of our other textures, we can see these. Now, again, these normal maps aren't perfect. They're not really correct because they're auto-generated. If this were a production environment, I would use normal maps that are not auto-generated, but that are sort of generated by hand. You know, the purpose is still illustrated pretty well. So anyway, with that is normal maps in our system. So we have a lot more interesting geometry and textures to look at here versus just sort of the normal stuff we've been working with so far, no pun intended. So with that, we're going to go ahead and wrap up here. Thank you guys so much for watching. Please toss the video a thumbs up if you liked it. If you haven't already, consider subscribing. Go ahead and hit the little bell icon there to get notifications as to when new videos in this or other series drops. And I will see you guys next time.